In this project, we decided to use a butterfly can opener as the item of choice. Here is an image of the can opener with some visible rust that we will talk about later. This type of can opener is commonly used for camping as it is simply constructed and easy to clean. Since carrying a heavy metal brick around with you as a can opener is often a poor packing choice when camping, reducing the weight of the can opener is important. Can openers are consistently in contact with water, soap, and salt, especially when camping. Because of this, corrosion resistance is an important factor in our material decisions. Since you do not want your can opener to break when camping at home, using durable materials is very important. A little bit about the item. So the can opener was made in the 1980s, and it was designed for rugged applications. There is visible evidence of corrosion, which is most likely iron oxide due to its orange color and flaky nature. The metal itself is made from an unknown alloy of stainless steel. Part of the device is painted blue surrounding the rivets, presumably as their protective mechanism. The two most likely causes of corrosion in this item are pitting and crevice corrosion. The reason for this is because the corrosion pattern on open areas of the surface visually resembles the dispersion of pitting corrosion. Likely causes of this are scratches and nicks in the metal surface. Concentration cells such as the diagram on the left-hand side can then form. The second corrosion occurring is crevice corrosion. As the rivet does not form a perfect seal against the surface of the metal, water can get in between the head of the rivet and the main body. This forms a concentration cell such as the diagram on the right depicts.
Based on the environment and use of the can opener, these requirements were created. The first requirement is that the rivet holding the two halves of the can opener must be able to support a load of 569.5 newtons. This load was determined using the average male grip strength of 38.7 kilograms and applying a safety factor of 1.5. The next requirement is that the handles must not deflect more than 5 millimeters when the maximum load is applied. This is for comfort of the user and ease of use. The objective is to minimize the mass of the can opener. This is to keep the cost as low as possible for consumers. Several constraints were also applied to the can opener. The handles were restricted to a length of 12 centimeters, which is the length of the original can opener and is an ideal length for a handle. The handles were also restricted to a mass of 100 grams each and the rivet to 30 grams, keeping the total mass under 230 grams for a light and low-cost can opener. The can opener must also have at least good resistance to corrosion to prevent excessive corrosion during use, and at least acceptable formability so that it can be shaped. It must be composed of less than 10 weight % nickel, as many people have allergic reactions to nickel, and the can opener is expected to be in frequent contact with skin and food. Finally, the cost of the material must be less than $6.52 per kilogram, which would make the cost of materials for the can opener $1.50 at the maximum mass.
In this MPI calculation, the goal was to reduce the weight of the can opener and get the strongest resulting metal at the same time. As a result, the MPI of shear strength versus density was chosen. Calculations were based on the strongest average grip strength in an average population, including a factor of safety of 1.5. Since the weakest point of the device is likely the rivet holding the bottom to the top sections of the body together, the dimensions of the rivet were used in the calculations. The second MPI was designed to allow minimal deflection under the average loading of the can opener while containing a low weight. Since the current can opener deflects by almost 10 to 15 millimeters, it can become apparent why increasing the rigidity is important. Having too much flex in the handle means that it is uncomfortable and unwieldy to use when cutting open stronger cans.
In addition to the MPIs, we added these limits. Corrosion resistance must be at least medium or good, formability must be at least acceptable, price must be less than $6.52 per kilogram, and nickel content must be less than 10%. Using the MPIs and limits, the only remaining material was annealed nitronic 60, which is an austenitic stain.
So we decided with some heat treatments for this part. It has been determined that the new design of the can opener needs a heat treatment process. The major reason for this is the cutting edge of the can opener must be harder and stronger than tin cans. However, tin cans are also made out of certain types of steel, so heat treatment is required to ensure the cutting surface remains sharp after repetitive use. There are multiple ways to heat treat metals to make them stronger and harder. Some more common ways were looked at and compared. and after this a final process was chosen. The first method to increase the strength and hardness is cold working, so repetitive deformation of the metal. Cold working increases dislocation density in the metal, creating new dislocations. The dislocations themselves prevent motion by interfering with other dislocation motion, and as a result, the cold working increases the strength of the material and also reduces its ductility. Adding the recovery stage of the annealing process after cold working will remove residual stresses caused by the cold working while maintaining the dislocation density or keeping its strength. And recovery also improves corrosion resistance by removing the possibility of stress corrosion. The second type of treatment that could be used is dispersion strengthening. This type of strengthening deals with dispersing a phase or precipitate throughout the material, which must be small enough to prevent dislocation movement. If strength and toughness are desired, the material should start off ductile and the phase added should be hard and brittle and dispersed uniformly. A higher concentration of these dispersed phases results in higher strength, so the phases should be small and numerous. Another type of heat treatment considered was aging. However, this type of treatment has certain requirements that must be met. First, the alloy must form a single phase when heating, then enter two-phase region when cooling. The material should be soft and ductile and form the hard and brittle precipitates after cooling. And lastly, the alloy must be quenchable and form coherent precipitates. Finally, quenching was discussed as a possible treatment of the metal. Since the metal is austenitic stainless steel, it has the capability of forming martensite as a result of quenching. However, problems may arise from quenching, such as retained austenite and quench cracks. Retained austenite causes more martensite to form during tempering, which results in the metal becoming more brittle. For stainless steel austenitic nitronic 60 annealed, retained austenite is not a problem since it mostly happens in higher carbon steels. This type only has 0.1% carbon. Quench cracks can also be avoided by heating the steel to a specific temperature so that when quenching occurs, the residual stress does not exceed the tensile strength. After reviewing the options and researching the material, quenching was found to be the best option. Stainless steel austenitic nitronic 60 annealed was found to not be heat treatable, and quenching came up as the only possibility for strengthening with heat. Based on further research, heating temperature before quenching is 1060 degrees Celsius and is quenched in water, not oil. And certain times that we found were approximately 2 to 3 hours of heating before the quench. In the manufacturing process, quenching would be done after the assembly of the entire can opener. The reason for this is that not only do we want the cutting edge to be hardened, but also the handle so it can resist bending. This process is simple as well, so it reduces the costs and steps in the manufacturing process.
The use of a can opener to open cans containing liquids, especially salted preservatives, makes it extremely susceptible to corrosion. In addition, the many crevices of a can opener are vulnerable to crevice corrosion. Due to the frequent contact of the can opener with food, it is important to prevent corrosion from occurring. There are 3 methods to avoid corrosion: removing the difference in electric potentials, removing physical contact, and removing the electrolyte. Galvanic corrosion occurs when there is a difference in electric potentials between 2 materials. This can be easily avoided by manufacturing the can opener out of only one material. However, a concentration cell may still form when liquid rests on the surface of the part. To prevent concentration cells, the presence of the electrolyte must be removed. A coating applied to the surface of the part removes contact with air, stopping charge transfer. Dursen by Silcotech can be used to improve the inertness, durability, fouling, and corrosion resistance of products ranging from precision instrumentation to severe industrial applications. The coating improves corrosion resistance and increases the hardness of the material, 2 important properties for a can opener. Dursen is low cost and food safe. Another effective way to reduce corrosion is to select the right material. Nitronic 60 contains a uniform distribution of nitrogen atoms, increasing the hardness and corrosion resistance of the material. This material has moderate to excellent resistance to corrosion in all environments. It does not require nitriding or carburizing. The only finishing process recommended for the can opener is the application of a Dursen coating to further protect against corrosion.